Welcome to Pass Academy. In this video, we're going to look at the hydrocarbon group alkanes. So first, let's define what alkanes are. Alkanes consist entirely of single carbon to carbon and carbon to hydrogen bonds. Alkanes are said to be saturated because the carbon atoms in the alkane chains have the maximum number of bonds they can have. So remember from our previous lessons that our carbon atom forms four hybridized orbitals, and in alkanes, these hybridized orbitals are used to form bonds with other atoms. So in this case, we have our carbon atom being bonded to hydrogen atoms. So because this central hydrogen atom has formed the maximum number of bonds it can form, we say that this carbon or this hydrocarbon is saturated. Let's move on to the names of alkenes. So alkenes are named according to the number of carbon atoms they have in their straight chain. So if we take a look at the first alkene we have here, it has one carbon atom and it is given the name methane. We name alkenes by adding the suffix "-ine" to the Greek word meat. So we have meat, and then we add the suffix "-ine" as in alkane. So we have alkane. So we take the suffix "-ine" and then we add it to the meat to give you methane. Likewise, in the second, we have an alkane with two carbon atoms. So the Greek word "eth" and then we add "-ine" to it to give you ethane. So it continues to, in this example, an alkane with 10 carbon atoms and it is named dec. So we have the Greek word dec for 10 and then we add "-ine", giving you decane. So let's move on to homologous series and molecular formulas of alkanes. So what do we mean by homologous series? Homologous series are families of chemical compounds that share the same functional group and similar properties. So what do we mean by this? It means if we have a group of chemical compounds and then they exhibit the same properties, for instance, boiling points, and then they exhibit the same chemical reactivity, then we say that these chemical compounds are homologous series. So we say the homologous series in alkenes or in hydrocarbons differ from each other by the methylene group. So methylene group given by CH2. So when we take a homologous series made up of alkanes, so let's say we have an alkane with 1 followed by an alkane with 2 carbon atoms, and then another with 3 carbon atoms. So we say these alkanes are homologous series, and then each molecule differ from its consecutive or successive molecule in a series by this methylene group. So what do we mean by this? It means to get to the next successive alkane, we would have to add CH2 to the previous alkane to give us this. And then if we should add CH2 to the CH4, we get C2H6. Likewise, if we should get to this, an alkane with 3 carbon atoms, we'd have to add CH2 to this, and then we have C3H8 to give us this. So each of these alkane molecules differ from their successive or consecutive member by a methylene group. And then if we have for an alkane, the general formula for finding the number of or the number of atoms an alkane contain is given by this, where the n is an integer. So let's say we have an alkene with 2 carbon atoms. How many hydrogen atoms do we have to add to this alkene to make it saturated? So we say we add 2 times 2 and then plus 2. So this will give us C2H6. And then we can also have an alkene with, let's say, 30 carbon atoms, and then we would have to add 2 times 30 plus 2, and so this will give us C30H62. So this formula is used in finding the number of carbon and hydrogen atoms that makes an alkene saturated. So let's continue to the drawing of alkanes. So alkanes can be drawn using 2 ways. We have the Lewis structure and the skeletal formula. So in the Lewis structure, as we've been using since the start of this lesson, the Lewis structure is simply drawing the carbon atoms and then bonding them to the various atoms that make up the alkene. So we can have this. So this is our Lewis structure. And then we have the skeletal formula. And for the skeletal formula, we draw straight lines like this, and each end and intersection represents a carbon atom. So we have one carbon atom here, we have another here, we have another here, here, and there. What if an we have an alkene, and then it is having a substituent which is not hydrogen? So in this case, because we don't have any um, substituents on either of these carbons, we take it as hydrogen. We take them as being bonded to hydrogens, so we don't have to write the hydrogens. We only write the skeletal formula, and then the hydrogens are omitted. But what if our alkane is bonded to other groups apart from hydrogen? So we would have to indicate the groups on the skeletal formula. So in this case, if this alkane is to be bonded to bromine, then we have to indicate it is bonded to bromine. And then if it is bonded to, let's say, an OH group, then we have to show it is bonded to an OH group. And then we can also have it being bonded to, let's say, um, a methylene or an alkyl group. So this is an alkyl group. So we can have our straight chain being bonded to an alkyl group. So let's continue to isomerism in alkanes. So alkanes containing 4 or more carbon atoms show structural isomerism. So what do we mean by this? It means if we have an alkane containing 4 or more carbon atoms, there are 2 or more structural formulas for each molecular formula. So we know our molecular formulas. For instance, we know our molecular formulas to be this. So if we have an alkane with N greater than or equal to 4, then there are 2 or more ways we can draw the structural formula of this particular alkane. So let's say we have an alkane. Let's take the first one, an alkane with 4 carbon atoms. So let's look at the various ways we can draw this. So using the skeletal formula, we have an alkene with 4 carbon atoms. So we have 1, 2, 3, and then 4. Then we can also have the structure of this alkene drawn this way. So we have 1 carbon atom here, 2, 3, and then 4. Let's move on to another alkene. Let's say we have an alkene C3 C5H12. So let's look at the various way we can draw the structure formula of this particular alkene. So we can have this. So we have one carbon atom here, two, three, four, and then five. Also have another structure being drawn this way. So we have one, two, three, five carbon atoms here. We can also have another structure this way. So we have one, two, three, four, and then five carbon atoms. So we can see that all these structures have the same molecular formula but different arrangements of the carbon atoms. So we can go ahead and then try writing the various structural formulas of this particular alkane. You can pause the video at this moment and then try your hands. So for an alkane with 6 carbon atoms, we can have this as the first structural formula. So let's say we have 1, 2, 3, 4, 5, 6 carbon atoms here. We can also have this as another structural formula. We can also have this as another structural formula. And then we can also have something like this. So we can also have another structural formula in this way. So we can see that all these structures have exactly 6 carbon atoms, and then they have different arrangements of these carbon atoms in space. Let's continue to alkyl groups. So we say alkyl groups are formed when a hydrogen atom is removed from an alkane chain. So the surface in an alkene is replaced by "-al" to indicate alkyl group. So if we have an alkene like this being methane, its alkyl group be this. We remove one hydrogen atom and this will be named methyl. Likewise, if we have this, if we have this being propane, its alkyl group, if we take one hydrogen atom off, we have this. So this is named propyl. So you can try for an alkane with 10 hydrogen atoms, carbon atoms, and then the name of this alkane is the cane. And if we take one hydrogen atom off, we have this. And the alkyl group name is given as the car, like that. So let's continue to the classification of the carbon atoms. So let's continue to the classification of carbon atoms. So carbon atoms are classified according to the number of carbon atoms they are bonded to. So we have primary carbon atoms, we have secondary carbon atoms, and then tertiary carbon atoms. So primary carbon atoms are bonded to just one carbon atom, and then secondary carbon atoms are bonded to two other carbon atoms, and tertiary carbon atoms are bonded to three other carbon atoms. So we write 1 degree to represent primary carbon, we write 2 degree to represent secondary, and 3 degree to represent tertiary. So if we have a structure like this, so if you have a structure like this, let's try and then identify the various classifications of carbon atoms in here. So we can see this very carbon atom is bonded to just one other carbon atom. So this is a primary carbon atom, and this carbon atom being bonded to two other carbon atoms. So this becomes a secondary carbon atom, and this particular one being bonded to three different carbon atoms. So we have a tertiary carbon atom here. And lastly, we have a primary carbon atom there. So you can try perhaps on this. So you can try and then find the various classifications of carbon atoms we have in this structure. So our first carbon atom here is bonded to just one other carbon atom. So we have a primary carbon atom here. And then over here, we have a secondary carbon atom. The next one, another secondary carbon atom, and a primary carbon atom as well. Let's move on to the IUPAC naming system of alkanes. So the IUPAC naming system follows rules, and the first is we have to name the longest chain. So when we are given the chain, we have to identify and then name the longest chain. After that, we identify the name groups attached to the main chain, and then we assign numbers to the groups by giving the substituents closest to the end of the chain the least possible number, and then we designate the locations of the substituents and their names. After that, we assemble the names alphabetically and then use prefixes such as di, tri, tetra when a substituent occurs more than once. So let's go ahead and then try examples. So in the case we have an alkene like this, so the rule says we should try and then find the longest chain. So we number our carbon atoms here, starting from the end here. We have 1, 2, 3, and then 4. And then let's try again and then number the carbon atoms to the other end. So we have 1 here, 2 here, 3, 4, 5. So 1 to 5 gives us the longest alkane chain, and for an alkane with 5 carbon atoms, it's known as pentane. And then we identify the substituents or the groups attached to the main chain. In this case, we have a carbon atom, an alkyl group being attached to this chain. And so we identify the substituent as a methyl, and then we find the location of this methyl. And what is the location? The location of this methyl is on the third carbon atom here. So on the third carbon atom, we identify, we give its location, and then we assemble the name. So let's try and then assemble this name. So this will give us 3-methyl pentane. So let's try another example. We have an alkane this way. So we have something like this. So let's try and then identify our longest chain. So we start the numbering from here. We have 1, 2, 3, 4, 5, 6, 7, and then 8. And then let's start from this end. We have 1, 2, 3, 4, 5, 6, 7. So obviously from 1 to 8 gives us the longest chain. So an alkane with 8 carbon atom is known as octane. And so we have an octane here. So let's try and then identify the substituents on this longest chain. So we have a substituent here. and then we have another one here. So these two substituents are all methyl. And then let's try and then give the locations of these substituents. So we from when we, the rule says we should give the least possible number to the substituent closest to the end. So this substituent compared to this is closest to the end. And so if we start numbering from our left to right, we have 1 here, 2 here. So the substituent is bonded to the third carbon atom here, and this is bonded to the fifth carbon atom. And then so we have 3 and then 5 methyl. So we have 3, 5 methyl. And then the rule says if the same substituent occurs twice, we use the prefix di as to indicate the same substituent occurs twice on the chain. So in the naming of this particular alkane, we have 3, 5 dimethyl octane as our cane. So we can try another example. So we have cane like this. So let's try and then name this particular alkene. So we first identify the longest chain. So we start numbering from here. We have 1, 3, 4, 5, 6, 7, and then 8. So obviously this gives us the longest chain. So we have another octane here. And then let's identify the substituents on this particular alkane. So we have a substituent here, and then we have another one here. And then as the rule states, we should give the least possible number to the substituent closest to the end. And this obviously is closest to the end. So it is on the third carbon atom, and then this on the fifth carbon atom. So our substituent is ethyl here, and then we have another ethyl here. So the same way, we have 3, 5 diethyl octane as our alkane. Let's move on to halogen substituents. Let's move on to halogen substituents. So we can have our alkanes having a halogen substituents on their straight chains. So if we have fluorine as a substituent, we call it fluoro, chlorine, chloro, bromine, bromo, and then iodine, iodo. So if we have an alkene like this with a bromine substituent, we first identify the straight chain. So we have 1, 2, 3, 4, 5 carbon atoms. So this gives us pentane. And then we assign the least possible number to our substituents. So in this case, if we number from here, from the left to the right, we have number 4 here. And then if we number from the right to the left, we have 1, 2, and so 2 obviously gives us the least possible number. So we have 2 bromo. And then we assemble our names together. So we have 2 pentane as our alkene. We can also have, for instance, bromine, 2 bromine atoms on the same straight chain. So as we saw in the previous namings, we use di to indicate we have 2 bromine substituents here, and so we name our straight chain. This gives us pentane, and then the locations of our substituents. We have 2 here and then 4 here, and so we have 2, 4 dibromopentane as our cane. We can also have an alkyl group with a halogen as substituents on a chain. So we can have an alkane chain and then an alkyl group and a halogen bonded to the hydrocarbon. So in this case, the rule says we should give emphasis to the alkyl group. What this means is we give the least possible number to the alkyl group before giving the other numbers to the halogen substituent. So in this case, we identify our longest chain. So we have 6, 7, 8. So this gives us octane. And then we give the least possible number to alkyl group. So we have the number 3 here, indicating the least possible number to this alkyl group, which is methyl. So we have 3 methyl, and then we have 6 bromo. And the rule says we should assemble our name alphabetically, and so we have 6 bromo, and then we have 3 methyl, and then we have octane. So this becomes the name of our alkane: 6 bromo, 3 methyl, octane.